So the interconnection needs to be decided either of the two types. Okay, now using the two types, uh, for the four different blocks we used, we'll make the following type of interconnection. Okay, that is, the first one is, we'll start with the input output. This was the IO port, input or output port, right? Then next we use what is called as the registers. Registers are used for storing the data. Since we are very specific about this design that we are going to use only 4-bit, right? This will be a, each register is of size 4-bit, right? Next to that we need a ALU, arithmetic logical unit, which performs all the arithmetics and logical operations. So this will be the ALU. Again, we are very specific, and hence we use 4-bit. Next to that, we have the shifter, right? This is called as a, you can use a barrel shifter or any other type of shifter, right? Let's call this as end around shifter, right? This shifter also needs to be of size 4-bit. Okay, so this is the shifter. So size 4-bit. All right. Now, what we do next is we take a line, and this line is expected to connect all the four devices, right? And the connection is going to be like this. So just see, either you use a specific type of the connection which already has been selected. Okay, already, if you see the previous case, there we actually have selected the type of what you call the interconnection, right? So we use the same thing now. So either one arrow mark going out or two arrow marks. So at the same time, now you can see the data which goes out from there will come into the device through this. Okay, so this is the type of connection that we want to make. Yes, and for every device we are expecting what is called as a control, right? So now let us apply the control to each device. Okay, so this control is what we call as the direction. Okay, this is the direction control. So direction control is whether you are reading from an input device or whether you are giving the data out to a external device. Okay, so that's the one. So this IO port will send the data in or out of this, right? From the IO port you always have a bidirectional arrow mark to the shift registers. Okay, because shift register may give the data to the output port, or the data may be read from the input port to the registers. Okay, and you see here the control which is required for these registers are, we will be calling them by the name select control. Okay, this is called as select control. So each of the device expects a control signal, right? Okay, and then you see the from the registers the data will directly go to the ALU, right? And ALU will have a control, and that control has a name called, we call it as operation control. Called operation control because ALU can do a lot of operations. Which operation needs to be done? It expects that input, right? Addition, subtraction, multiplication, right? Logical and or anything. Even the shifter expects a control, but the data from ALU directly comes into this shifter, and the shifter expects another input as a control signal, and that control is called as the shifting control. So you see, it can be this control signal, shifting control may be in terms of what is the direction of shift, okay, in which direction you want to shift the signal, etc. Right? Are you going to do a right shift? Are you going to perform a left shift? Or right, anything like that. Okay, so that's the control that is offered by this. Right. Once this is done, now the next step is to perform what is called as a floor planning. Right. This is to perform the relative disposition of the subunits on the chip. Right. So now I know the block diagram, but this has to go onto a chip. Right. So that will be your next step in the design. Right. Right. Then we are going to perform a tentative floor plan. Right, this should show, right, or I can write showing the planned relative disposition of all the units, okay, of the, I can call it as a sub units on the chip. Why do you need this? This is required because you need to prepare several masks. So in the process of manufacturing of a different types of MOSFETs, we know that there are several masks used. Very similar to those masks, you need a bigger size masks to be prepared so that you perform layer by layer manufacturing of the whole chip. All right. So that is why it is required. Okay. You need a proper layout to get the masks prepared beforehand you start with the process. Okay, so in this, what we do now is uh, we have to decide about the architecture of the bus linking the subunits. So we know that there are so many subunits, right? Each subunit can be connected to one another using the one of the several available bus architectures. Bus architectures are basically the number of buses you use in the system, right? Bus is what? It's a set of lines carry the data or the address or the control signal, correct? So that's what is called as a bus. Now, what type of bus architecture you are going to use for your system that you are designing, right? Needs to be decided now. So that will be the next step, right? So we need to decide the architecture of the bus that actually links the sub units, right? It is normally, right, you have three options. The first option is okay, I'll write it as a side heading so that we can write even the block diagram corresponding to that. So the first one is called as, this is one bus architecture. Okay, so one bus architecture is the simplest one, right? So if you want to write a simple block diagram showing this, so the first one, let's consider this to be a register. Let's consider all the registers. Registers followed by, let's say we have the ALU. Okay, and the ALU is actually connected to, let us say, a shifter. Okay, now The data, I can use only one bus, single bus. Okay. So the single bus will be connecting each and every device. It's actually, you can see that this is how it is getting connected. It's connected, ALU is connected to the shifter, and the shifter is in turn connected to this. You can see the diagram corresponding to the one bus architecture where a single bus is used to connect all the blocks. Basically, registers are the ones which hold the data here, and that data will be passed on to the ALU. ALU, right, will perform the required operations on the data, and result will be first shifted to the shifters. Shifters are used to hold them temporarily before they are transferred back to the registers where the data can be stored. So this is how the working of a one bus architecture system is going to be. All right, so we'll write them quickly. So let us say we have a operation, maybe addition of two 4-bit numbers. Now how you are going to carry that? This is how. First, you take the one of the operand. So I'll write first operand from registers to ALU. It will be moved from this, and it is stored there. Okay. So first operand will be read from the registers. It will be stored in the ALU. Now we need to take out the second operand that's also assumed to be present in the register itself. Okay, so then we go for the second operand, right? From, you take it from the registers. You don't have to save because already there is one of the operand is present over there. What you can do, right, you perform the ALU operation whichever is required, correct? Because ALU, maybe the question is to perform addition, right? So ALU operation, once you perform the operation you get the result, right? And the result will be first stored in the ALU. Okay, perform the ALU operation, result in ALU. This is the step number 2 of this kind of architecture, right? And in the third step, what you do, result will be passed through the shifter to the register and gets stored over there. Result is passed to registers through what? Through shifters. Through shifter and stored. So this is the first type of architecture that is called as one bus architecture. All right, and the second type is called as the two bus architecture. No, three. the one example which we considered earlier was a three bus architecture. We wrote three different buses, correct? As you can see here, control bus, address bus, and the data bus. That's the three bus architecture, right? Anyway, so in two bus architecture, we are going to use two different buses. So the advantage being more paths for the data transfer. When you have more paths, you can perform the operations quickly. Okay, so that's the only intention of adding another bus to this architecture. Okay, so to start with, let's consider the same three blocks. So the block number one is for its registers. Second block is the ALU, and third block is the shifter. Okay, so we have the three blocks. Now we'll make the connections to this by using two different buses. Okay, so the first bus that I'm going to use, let me write over here. This is the bus number one. All right, similarly, let's use a bus number two as well. Okay, so this is the second bus, and the connections are going to be made in the following fashion. So let me call the upper bus as a, this is bus A, and this is bus B. So we will not assign any name, whether it's going to carry the data only or the address, etc. We are not going to look at that aspect now. We have to use two buses for the communication ultimately. Okay, so now let's connect the registers to the bus B, and from this bus we are connecting to ALU. ALU will pass on the data, and let's use a bidirectional arrow from register and bus A, and from bus A to ALU. Okay, and we need another specific connection here. This is to put the result back. Okay, we have a different connection now, and if something has to be read from bus, we use this line, and if you want something to move from shifter back to any other place, you use this line. Okay, now let me name the size specifically. Okay, so this is a 4-bit bus, and the, okay, we'll call this is maybe A, this is B. Also, by using a 4-bit bus, I'm going to call the result as S, which will be stored back using this, and this is in, and this is an out operation. Okay, now you can see that ALU is going to perform the read operation using two lines, two different lines. So this is more faster compared to the previous case. Just see here, one of the operand will come from this path, right? That is A. The second operand will come from this path. Now you see it is faster, right? Both can be done parallelly. You don't have to wait. When you consider the previous one bus architecture, one operand will come, it will get stored, then the second operand will come. You see that there is a delay, right, in reading the two operands in case of a one bus architecture, but that has been eliminated here because you are using two different buses. All right, so that's the first point which we can write in this. Both operands So in this case, I have taken example as A and B. Okay, both A and B operands are sent from where? From registers. You are sending them from registers to ALU. Directly they will come. You don't have to store, right? As soon as they reach, you don't have to store it. Directly you can perform the ALU operation, right? Carry out the ALU operation and store result, that is denoted by S in the block diagram, in ALU first. Temporarily you will store it in ALU, but you see that result is passed right through the shifter and it will go back to the register. So which is the that path? We know that now also it has to pass through the shifter only before it goes back to the register. In the sense, I don't have, see, the S is available here. It will not go back in this path. It's not allowed, right? As per this architecture, it has to enter this result S which is there, will go through the shifter and then it goes back to the register. So in this two bus architecture, right, we follow this particular technique. All right. So then in the last step, you can see that result S is passed to the register through what? Through shifter. And gets stored. All right. Then the next architecture is 3-bus. Okay, so the 3-bus architecture will follow the following representation. So we have the first block. This is for registers. Then we have ALU followed by shifters. Okay, now we are going to use 3 buses. Okay, this will be bus number 1. This is bus number 2, and we use a 3rd bus. Yeah, any one of them, any one you can use. Okay. The other diagram which we draw, we had drawn earlier, right? That used a 3-bit structure. Okay. 4-bit, correct. 3-bus architecture, right? Okay. First connection, second connection. Okay. This is the third connection, and this goes out, this comes in. This is going in. All right. Then there is a connection like this. It's going in here, and this is connected like this, and The last connection will be like this. Okay, now let's give the name here. Say this is bus A, bus B, and bus C. All right. Now, you can see here from, let's say, registers, you use 4-bit buses. Okay, so this will be a 4-bit 4-bit bus. So using this 4-bit bus, one of the operand will go from registers to ALU. So I'm going to call that as A, and the second 4-bit bus is going to carry the operand B. Both of them will reach ALU at once, and they get added up, or any ALU operation, to produce a result S. Now you don't have to wait, it will directly pass on to the shifter independently, and shifter will pass that back to the register. Meanwhile, the second operation can happen simultaneously because you don't have to wait, because at a given point of time one bus can carry one data. If you have a single bus, that's the problem. Single bus can carry only one data at a time. Two bus system can carry two simultaneously, but three bus means three things can be done simultaneously. Reading as well as writing can happen simultaneously, so you save a lot of time here. Okay, so that's the uh, advantage of three bus architecture, right? So most of the designs systems will use the same. Okay, now let's write them quickly. So both operands are sent from registers. Okay, registers, both are sent from registers to ALU. As soon as you receive them, you can simply perform the ALU operation. Correct? Yeah. Perform ALU operation. So you don't have to wait. It's everything happens in a single step here. You see so many lines are available so that you can pass on the data while you operate on another data. Next is data set might come through A and B. Meanwhile, you can pass on this data back to the registers using a different line which is available. Right? So you don't have to write here step by step. It's everything is happening in a single step. Okay. Operation, comma, shifted result S is returned to what? To register. Uh, using what? Using a third bus, right? What is important? Everything happens simultaneously. We just have to remember that, okay, this is how it's happening. Everything will run simultaneously. So that's the importance of three bus architecture. Fine. Now we are still in the general arrangement of a 4-bit arithmetic processor. So as a previous step, you have to choose one of these three uh, bus architectures for your design, right? We did that. Let's assume, okay, we have chosen one of them and we did that. Okay, so each of this architecture will have its own advantage and a disadvantage. Okay, right. Now maybe you assume that, okay, we have selected one of the bus architecture, one bus, two bus, or three bus architecture you have chosen here. Okay, right. Once you choose that, now we can plan the interconnection strategy by planning the power rails. So this will be the next point when you in the design. Okay, right. After you choose the data interconnection, right, using one of the previously available data paths. Next thing is, right, uh, to plan the interconnection to plan the interconnections strategy by planning for the power rails. It indicates where will be the lines of power supply, right, go through your circuit, which parts of the circuits will get the direct access to the power supply. This is very important because the circuit components which require higher power or high power dissipation, you want to keep them close to the power supply. Okay, right. Power rails, and you also do one more thing, that is roughly making basic allocation of layers on which different signal paths will be routed in the circuit. Okay, so and we can write like this: roughly making some basic allocation of the layers. Okay, different layers. Now we know that the circuits are built up in layers, right? So different layers you allocate on which the different signal paths will be routed. Okay, now this means uh, whatever plan you make in this step, this actually includes the necessary IO interface, right, to the parent system of the data bus, right, for a given architecture, right. So this is what is required. Now I have to make sure that there is what is called as a system bus, the main bus which connects to the main system, in the sense whatever processor you are designing, this will be connected to something else, right. So that is considered as the system data bus, main bus. So your system which you are designing now should get connected to that. How do you decide that? How do you connect your system, the processor which you are designing now, how do you connect this to the main bus, is what is the question. So that has to be done through which block? It has to be the IO block, correct? Because for your processor, the other systems will look like either an input device or an output device. So it has to connect to that using a IO device only. So we'll write that point before we write the next diagram. Okay, so this plan includes the necessary IO input output interface to what? To the parent system. To the parent system in terms of the data bus. To parent system data bus. Right? Now we'll go for the diagram showing this aspect. Okay, now let's draw another diagram now. This is again a rough estimate of what is happening. So let me say this is the overall boundary of my system. Fine. Now I have okay, I'll use different colors to highlight different types of connections. So I'm going to use say green color for control. Okay, so I need one control line over here. So this is say one of the control. I'll give a name later. Okay, and we need two more controls over here. This is the next control line and another control line over here. Okay, so maybe this one. Okay, so three control lines over. Now I use the data and the power, because you see that the power lines are also included in the previous step, right? So I'll use a power line using the red color, right? So the power lines will flow in my uh, system, maybe somewhere here. Okay, here my intention is just to show that what will be done at what step. Okay, so in this step we are supposed to do this. Now why exactly this step, I don't have answer, because it's left to the designer. He can place it anywhere. Okay, right. So same thing, I use another different color for my maybe the data. Okay, so data I use bidirectional, just to indicate that I want to have a bidirectional data communication. So maybe this is the data. Okay, all right. Now let me give the okay, let me write the names so that this becomes easier. So I have, this is the bus number one, red color, and this is the black bus number two. Now you see how the blocks are connected. So on this side I have IO, then I have the block is in here. Okay, anyway, I'm not writing the block, I'm just showing the positions. What are the buses available for each of the device? See, 4-bit okay, sorry, I'll write the name completely. This is 4-bit register. So you can see this register will get a power supply. It will get connected to the control lines. The vertical lines are control lines, green color, and it also has an access to this data bus. That's what is the meaning of this diagram. Okay, so each of the block, right, they have each of the block, you can see that what access, what type of access, right, each of the block has with respect to these three buses. Okay, right. Then in the next step you can see that I'm going to write the next block. This is the most important block of ALU. You see everything is available here. On the above you have the power supply, both sides you have control lines, and the bottom you have the data lines, right? And at the end you have the 4-bit the shifter. In addition to this, now we know that there is what is called as the main, the parent system's data, right, data bus. So that will be somewhere here, let's assume. So this is the data bus of the parent system. Okay, I'll write here, this is parent system, say data bus, right, which means there has to be a technique to access them through IO. So you see the IO is actually connected in this way, right? So parent system's data bus is connected to through IO. Whichever IO interface you are using, you can use it to access this. This is what has been mentioned in the earlier. It includes the necessary IO interface to the parent system data bus. So you have to show that here. Okay, so using this you are connecting your whole system to the main data bus, which is the data bus of the parent system. Okay, so this is a very basic floor plan. Now, in the next step, these floor plans sketched at the early stage of the whole design, right, could be tentative because you still don't have very accurate access to the area requirement. How much area is required for a 4-bit register? I don't know. How much area is required for a 4-bit shifter? Also, we don't know, right? But we know that okay, this is where I'm going to place throughout, right? And after this, once this is done, now we'll go for the allocation of different layers. When you know all of them, you can go ahead and make the exact allocation of area, right? Let's assume that that is done only after you know the specific area requirements of each of the blocks, correct? Yeah. Right, so I'll write next as per the accurate area requirement of each block, the floor plan is finalized. You finalize. Okay, this is how it has to be done. Once it is done, right? Next, you need to allocate different layers, right? Yeah. Then the allocation of different layers to data or address or the control parts, allocation of different layers of this parts should be done using the following facts, right? This is the last point what we are writing now. This has I think 5 6 facts to be considered. Okay, so this is the point number one, the fact number one. This is an interconnection is formed when lines touch each other at same level. Whenever two lines touch at the same level, that means you need to make a interconnection over there. This point should be remembered. Okay. Next, right? If you have two different layers, polysilicon and a diffusion, and if at all they cross each other, means there is a transistor. Okay, this is possible even for a second layer, third layer, or whatever number of layers. So should be taking, we should take care that only wherever, whichever position you expect a transistor, then only polysilicon crosses diffusion, right? Very important. Most of the time we make mistakes over here. So a transistor is formed whenever polysilicon crosses diffusion. This is, as I told, it's very important. Then whenever you are performing the layer wise operation, all these points are important. Okay, now poly or a diffusion can cross metal. Okay, crossing off, I can write it in this way: crossing off a poly or diffusion by metal. Metal layer can cross any of them. Metal is allowed. Right. Next, fourth one, the diffusion or the polysilicon can be joined to metal. Okay, you can at any point you want to have a contact, you can do this. This is also allowed. Okay, this actually comes in the second chapter, right? Why and how this gets done, etc. In the concepts of developing different regions. Okay, then the next one, if at all you want to have a connection between diffusion and polysilicon, right, you have to remember that there has to be a buried contact. Without that you cannot connect diffusion and poly. Diffusion and poly can be joined by using what is called as a buried, B-U-R-I-E-D, buried contact. Okay, there is another type of contact that is available. First one is buried, and if that is not possible, sometimes you use another called as butting, B-U-T-T-I-N-G, contact. Either of them can be used because they will be located at different layers. You have to make a connection between the layers here. Okay, that's why. If at all a second metal layer is available using a double metal process, right, you see that whenever two metals cross, right, there can be a possibility of what is a contact, right? So should be very careful over there. So two metal layers can be joined. If you want to join, you have to use what is called as a via, VIA. So this is the next point. So two metal layers can be joined by using the wire. Okay, and coming to the CMOS, complementary MOS architectures, if you have a NMOS and PMOS diffusion wires, right, they should not cross N well and P well because there is a boundary limit for that. Anyway, we know that it never happens, but I just mentioned here. And uh, electrical properties of each layer should be taken care, right? Maybe one of the layer is more conductive, second one creates more magnetic field, something, some properties will be there, right? You need to take care of them before you use them as a layer in your design. Okay, other 2 points are extra, whatever I told, right? So normally this could be up to a 6 mark question. Only the last part can come as an individual 6 mark question, so for which we have given 6 different points. All right, so as whole, starting from the beginning, this can come up to 10 to 12 mark question if possible. Okay, right. So that is a complete process. And in the coming class, we will be starting with the design of a 4-bit shifter.